Welcome to Maths and Science by IITian channel. In this lecture, I will be taking up the potential energy V, and from the potential of a particle, how we can get the angular frequency. Angular frequency omega is equal to square root of 1 by I d square y by d theta square, where V is the potential energy and I is the moment of inertia and theta is the angle. And L is the length of the string, because in the last class I have discussed about the simple pendulum compared with the conical pendulum. In that class only I have promised that we will be switching over to for some lectures on Lagrangian and Hamiltonian. These are the two approaches to solve the difficult questions in classical mechanics, especially mechanics, because mechanics is one of the toughest sciences in physics, along with quantum mechanics, quantum physics we can call. Mechanics is very tough. In mechanics, till now we have dealt with Newton's laws, where we have dealt with force, acceleration, velocity and all these vectors. In Lagrangian and Hamiltonian, we will not deal with the force, we will be dealing with energy, which I have explained in the previous class. Please look at it on simple pendulum and conical pendulum when I have compared. This energy is a scalar quantity, it is not a vector quantity. So that dealing with scalar quantities and energy principles, conservation of energy, some may find it easier to apply. Hence, Lagrangian methods, Lagrangian approach, Hamiltonian approach for solving typical mechanics problems, I will be introducing. As I promised in the previous lecture, I want to take up the first case as the simple pendulum, because where simple pendulum, the energy is involved. There is a variation of the energy from potential to kinetic, kinetic to potential. How it varies, and when it varies, how to find out the angular frequency. I will give the brief only, I will not derive all the equations, I will give the brief so that you will feel the feel of angular frequency when potential is known. In the examinations, we need not only think that frequency from t is equal to 2 pi into square root of L by G only, frequency may be asked. No, there can be from potential, if frequency is asked, this type of formula we have to apply. Now, it is a little bit advanced topic, please try to understand. It is an easy topic, easy way to solve the mechanics problems. If you apply it, try to understand carefully, try to understand with due attention. See my lecture with due attention till the end. Now, in simple pendulum, the question is how omega, the angular frequency, be represented under equilibrium conditions when potential, V is potential, when potential is given. With respect to angle theta. This is our question. How we have to do it? You just see, it's a simple pendulum. And in the initial stages, the simple pendulum bob is here. This is the bob. And this is the maximum length of the string. And let this be L, length of the string. And this will be, bob is mass M, so that this is the mg. Then, please try to understand. This is, let us say, A, this is B. What is the length of AB? When the angle is theta. The horizontal distance between the vertical position of the bob and position at angle theta. This, let us say A, this is O. OB is equal to, please try to understand this carefully, OB is equal to L. Then, adjacent side OA by hypotenuse OB is equal to cos theta. That means OA is equal to OB is equal to L. So that OA is equal to L cos theta. Do you agree? This total distance, because it is a circular path, it is making vertical circle, vertical oscillation. It is making a vertical oscillation. When this is L, OA is equal to L, then let us say it is C. OC is equal to L. OC is equal to L. Then, what is AC then? AC is equal to, that I have already told you in the previous class, previous lecture. This is delta H. AC is equal to delta H. Change in height. The delta H is equal to OC minus OA. OC minus OA. That is equal to L minus L cos theta. That implies AC is equal to delta H is equal to L into 1 minus cos theta. This is a very important equation. Please, if you want, you write down, solve on yourself. This is a very important equation. The change in the vertical position of a particular object, here object is a bob of mass M, is delta H. What is potential energy? Potential energy is equal to, it is represented by V, that is equal to, it is represented usually in physics by V, that is equal to mg into delta H. This is also very important concept. Whenever potential energy increases or when potential energy becomes the highest, then kinetic energy becomes the lowest. Because as per conservation of energy principle implies kinetic energy plus potential energy is equal to constant. Now you tell me, at position B, potential energy is the highest. Observations, let us make the observations first. 1. At B, potential energy is equal to maximum, which implies kinetic energy is equal to minimum. Or it can be, if it is at rest at B, then kinetic energy is 0 also, because kinetic energy depends upon velocity. Potential energy depends on position. Change in velocity, change in position. Now, P is maximum. Then, second, we are interested at C. At C, that is at the bottommost point. Potential energy is the minimum, implies kinetic energy is equal to maximum. That means velocity maximum. That means angular velocity maximum. Whereas potential energy minimum means it can be 0 also. Delta H is equal to minimum, or delta H is equal to 0 at C. At B, delta H is maximum. At C, delta H is minimum or 0. At B, kinetic energy either minimum or 0, and kinetic energy is maximum at C. These are the principles which are used in Lagrangian. Lagrangian approach for solving mechanics problems. Critical problems in rigid body motion, three rigid bodies are there. There is a pendulum is there, compound pendulum is there. There are two pendulums hung from a rod like this. This is one pendulum. This is another pendulum here. Mass m1, here mass m2, and this rod is moving with some velocity or acceleration. Then how these pendulums behave, their oscillations. These are all very typical questions, very tough questions in physics. They cannot be that easily answered by resolving in forces. There should be a simple mechanism. That simple mechanism is through energy conservation principles. Now, when we come back to our simple pendulum, my oscillation is depending upon theta, because if there is a variable, that variable should be that energy or whatever quantity you are going to find, that can be found on the basis of certain energy, certain variable. Here I am taking theta, angle as the variable. Angle is equal to variable, and this is L. This angle is changing with time. In the initial time at t is equal to 0, it is like this. At some t is equal to some t1, the angle will be theta 1. At t is equal to some t2, angle is theta 2. Like this, angle is changing. My length of the string is not changing, angle is changing. It is the initial position. From the initial position, when it starts swinging, the angle is changing with time. Here, d theta by dt is equal to my angular frequency, angular velocity, which I have explained in initial classes of rigid body motion or rotational motion, that is equal to omega. D square theta by dt square is equal to alpha, that is angular acceleration. Like dx by dt is equal to linear velocity, d square x by dt square is equal to linear acceleration. In the similar way, dx by dt is equal to v, d square x by dt square is equal to a, acceleration. This is velocity, this is acceleration, not capital V. Capital V is equal to potential in mechanics. In electricity and magnetism, capital V will be volt. It is potential here, we call it as a potential. Now, under equilibrium conditions, I am not going to derive the equation, but rather I will present the equation so that with this background you can understand the equation well. The equation given in the case of a simple pendulum, omega angular frequency is equal to square root of 1 by I into d square v by d theta square. Because V is the potential energy is changing with respect to time, with respect to theta. This is very important equation relating angular frequency and potential energy. Now, under equilibrium conditions, here I have given V theta, variable is theta with respect to, there can be Vx also. Vx is variable x with respect to x, distance. Here it is with respect to angle theta, because theta and x are related. How theta and x are related? X is equal to the distance. How it is related? It is related L into 1 minus cos theta. Please remember, this is the simple pendulum. This is L. This is L. This total. And this height we are interested in. This is delta h we are interested in. This delta h, or we can call it as a distance x. Then x is equal to L into 1 minus cos theta. If theta is 0, x is equal to 0. If theta is equal to 0, it implies x is equal to 0, or delta h is equal to 0. If theta is equal to 90 degrees, x is equal to L. or delta H is equal to L. That is in this position. In which position? The pendulum will be in this position. This is L. Angle is 90 degrees. This is the logic behind this equation. That means potential can be varying with respect to angle V theta or Vx. Either way, we can write V theta potential is equal to mg into delta H is equal to mg into L into 1 minus cos theta. Do you agree to it? Please remember this equation, very important for simple pendulum. I am only talking about the simple pendulum now, not beyond that. What will be the first derivative? dV by d theta is equal to d by d theta of mg L into 1 minus cos theta. I think everybody should be able to do little bit of derivatives, simple derivatives. That is equal to d by d theta of mgl minus d by d theta of mgl cos theta. That is d by d theta of mgl is 0, d by d theta of constant is 0, minus d by d theta of mgl, you can take it out constant, d by d theta of cos theta is minus sin theta. That is equal to mgl sin theta. dV by d theta is equal to torque. Please see how many terms we are getting. Restoring torque. Restoring torque we call it as mgl sin theta, because system should be in equilibrium. For system should be in equilibrium, there should be restoring forces and restoring torques. dV by d theta is equal to restoring torque is equal to mgl by mgl sin theta. dV by, please remember this, is equal to restoring torque is equal to mgl into sin theta. This is another equation. Now, let us differentiate this equation again. What happens? d square v by d theta square is equal to mgl into d by d theta of sin theta. Agreed? d by d theta of sin theta is cos theta. That is equal to mgl cos theta. That means what we have got here is, first equation is V is equal to mg L 1 minus cos theta. This is with respect to theta only. dV by d theta, this is equal to potential energy with respect to theta. And dV by d theta is equal to mgl sin theta, that is equal to restoring torque. Third, d square V by d theta square is equal to mgl cos theta, that is equal to we call it as stiffness. Please remember this. These are the three important formulae from potential energy for a simple pendulum. Here we have not used any force. Please understand. These are the formulae we have got. This is mgl cos theta is the stiffness. dV by d theta is mgl sin theta is restoring torque. mgl into 1 minus cos theta is a potential energy. Now, what is the angular frequency? I will give the formula. Potential energy when theta is equal to 0, that will be the minimum at the bottom of the swing. Here, and stiffness d square v by d theta square when theta is equal to 0, what is its value? mgl into cos 0. When I put a line, vertical line, and write this, that means I am writing the value of the variable d theta square, that theta is equal to 0 at what point? That is equal to mgl. Theta is equal to 0 is called as equilibrium position. Equilibrium position. Please try to understand. That means d square v by d theta square is equal to mgl at equilibrium position. Theta is equal to 0. This is what we have arrived at from the above. Now, the equation given is omega is equal to, angular frequency is equal to square root of 1 divided by I d square v by d theta square at theta is equal to 0. This is the equation, angular frequency. Please remember this for a simple pendulum. That is equal to square root of 1 divided by I. D square v by d theta square, what is the value? mgl at theta is equal to 0. This should be at theta is equal to 0. That means, can I replace this value with mgl? That implies omega is equal to square root of mgl by I. What is the I? For the given conditions, the moment of inertia is equal to ml square for the simple pendulum arrangement. Please remember this. Please replace this value here. Then omega is equal to square root of mgl by ml square. That is equal to square root of G by L. Here if you see, for deriving this, we have not used any forces, any components of the forces. We have not used any vectors. We have just simply found out the derivatives and simply substituted the values. Therefore, omega of a simple pendulum will be square root of G by L which implies T is equal to 2 pi into square root of L by G, because T is equal to 2 pi by omega. This also I have explained in the last class. Please remember this one. Hence, what we have got here, many concepts we have developed. One is that these three concepts, V is equal to mg L into 1 minus cos theta, potential energy, du by d theta, restoring task, d square V by d theta square as a stiffness, and from omega is equal to what we have got, main equation as V is equal to mgl into 1 minus cos theta. From here we have got omega is equal to square root of 1 by I into d square V by d theta square at theta is equal to 0 is equal to square root of G by L, and from there we got T is equal to 2 pi into square root of L by G. In 3 steps we have got the value of time period and angular frequency of a simple pendulum with the conservation of energy principles. Here V is equal to potential energy, dV by d theta is restoring torque, d square V by d theta square is stiffness. Please remember them. With this, I want to conclude this lecture, and if you feel there is a value addition, this Lagrangian method will be more useful when you go into the real mechanics of these pulley systems and then inclined plane problems. Many problems in mechanics can be solved without involving the vectors and without involving the forces. With simple methods of energy conservation, we will be able to solve the, and also complicated problems like double pendulum, as I told you, and pendulum is moving, and another thing is dumbbell you might have seen, double pendulum. When you go to gym, there will be dumbbells, it will be like this. 2 iron balls will be there, they are connected by a rigid long iron rod. These are spheres, and this is iron stiff rod. Then double pendulum, as I told you, pendulum like this, moving with some velocity or acceleration, and like this many rigid body problems. It's a rigid body, double pendulum is a rigid body, dumbbell is a rigid body. It will be very difficult for us to solve them when we adopt the force and vectors method. It will be easy when you go through the energy conservation principles and Lagrangian and Hamiltonian approach. It is called as Lagrangian approach. I have given a brief of it, and when I deal with Lagrangians, it's an advanced topic. When I start the Lagrangians, maybe after a couple of lectures on rigid body motion, then couple of lectures or 3-4 lectures, then we will move to Lagrangians. Then we apply Lagrangians to every principle of mechanics, in starting from simple principles of what you call inclined plane motion. Everything depends upon the equations of motion in mechanics. Best of luck to everybody. Thank you for listening to me. I want to stop this lecture now. It's become a little bit lengthy, but try to see it. If you want to understand the Lagrangians clearly and simple pendulum mechanism, try to see the video, repeat the video if required. Kindly share my videos if there is a value addition, and subscribe to my channel Maths and Science by IITian. My channel name is Maths and Science by IITian. Thank you. Best of luck.